no. Sorry? Somebody said something. A recording in progress. Yes, recording is in progress. Thank you. All right. Any other announcements? Earth and Space Exploration Day is going to be virtual on, I forget what the date was, November 13th. That's the... No announcements from CC leadership. All right. So with that, I will turn it over to Amanda to introduce our visitor.
Hi, everyone. In case you don't know me, I'm Amanda Clark. I'm in faculty in CC, and it's good to see so many grad students and undergrads here. One announcement is for those of you who signed up for dinner, please stay after and we can make the plan. And for those of you who are interested in speaking with Laura, there are still some slots tomorrow where you could chat with her about her science and her career. So I'm really happy to have Laura here. It's been really fun chatting with her. She has a background in geology with a planetary science focus and an undergraduate in mathematics as well from Pomona College. And then she spent some time at Brown University where she did a master's in both geology and a master's in engineering fluid mechanics, which really formed the foundation for a lot of her later research. She did some fun projects while she was doing fluid mechanics, where she worked a little bit on an applied project related to windmills. So that's kind of fun. And then her PhD was also from Brown, and she worked with Jim Head. And she largely worked on explosive volcanism and pyroclastic deposits on both Mars and Mercury. And she's one of the few people in planetary science really working in explosive volcanism, especially sort of at the time that she did her PhD. In order to then look at sort of, instead of just ash dispersal, but into atmospheric dynamics on other planetary bodies, she studied it with a group in Paris where she did a postdoc working on a general circulation model that it was designed for Mars atmospheres. And she continues to work on that in her current research. She's been at JPL for 7 years, is that right? So as a research scientist, permanent staff member. And she's done a lot of different projects there, including what she'll talk about today. And she is also part of the, let's see, you were the deputy project scientist of the Mars Odyssey project. And then also this mission concept that she'll talk about today. She and I have also worked together on proposals related to multispectral imaging of pyroclastic deposits on Earth with the idea of extending those applications to planetary bodies. And she is also an avid field scientist. So she's always going to new places to see new geology in order to enrich her knowledge of planetary surfaces. So with that, I'll leave it to Laura, and this will be a fun talk.
Okay, can you hear me? Good, okay. So thank you very much, and I'm so glad to be here. For me, it's, I think, the first time I've traveled for work since probably February of 2020. So today I'm going to be talking to you about this mission concept called Moondever, and the idea behind Moondever is to go inside a lunar pit and explore in there. So I'll tell you, I was thinking about calling this talk, it's called Geological Delights and Engineering Challenges. I could have just as easily called it Geological Challenges and Engineering Delights. So you'll see what I mean. So in about 2009, a mysterious hole in the moon was discovered by the Japanese spacecraft Selene. These pictures are from ASU's own LROC camera. If you're familiar with that camera, taking beautiful pictures of the moon and many oblique pictures, this is one particular pit in the moon in Mare Tranquilitatis that we'll talk about a lot today. So when people first saw this image, it led to a lot of press speculation. First of all, just, wow, there's a hole in the moon. I mean, seriously, there's a hole in the moon. And then holes in the moon, there could be hidden tunnels below. There were TED Talks about it. There was actually a country song that somebody wrote about it. How about them holes in the moon? And then people started thinking about, wow, if you have a hole in the moon in this giant, potentially giant subterranean cavern, then what could you put down there? You could put an astronaut base. And it's kind of nice down there because it's protected from radiation and micrometeorites and extreme temperature swings. So they thought, well, that could be nice. Like, oh yeah, let's put a moon base down there. You know, it's great. We're totally going to go there. And then, so kind of out towards the fringes of the internet, there were people being like, well, there's things you could put down there, but what if there's things already there? And so there are a lot of ideas about what could already be hidden in this moon cave, as it's probably the one place in the solar system where you could put something and it would last for a couple billion years. So one of the craziest theories that I saw was the hollow moon theory, which is that is the moon hiding a hollow core? And the idea is that the entire moon is like a spacecraft, and this hole could be like the entrance to that spacecraft. So I always like to tell people, like, don't worry, NASA has checked, the moon is not hollow. So this just give you a little background on this particular pit. This is about how big it is. I've superposed this local football field from Pasadena onto the hole. And then I also superposed it on top of JPL here so that you can see it subsumes the entire cafeteria and everywhere else that JPLers go to get coffee and food. And then if you look about how deep it is, I tried to choose some examples, Big Ben there and the Statue of Liberty. And then I have actually, it's deeper than the Saturn V is tall, and the SLS Block 2 could also fit inside this hole. So you could use it like a missile silo, just launch the rocket right out of the hole. And then my other frame of reference is about 20 giraffes deep, if they all stood on each other's heads. To give you a more concrete example of how large this hole is, this is a very similar structure made in the same way. It's a collapse pit in Hawaii called the Devil's Throat. And across the way, you can see this tiny yellow person. That's Anna Zena, my friend. And she, this hole, the one on the moon is about twice as wide across and more than twice as deep. So it's an enormous hole. And this is kind of how those are made. People talk about these as skylights a lot, which skylights are usually like a lava tube, and then there's a hole in the lava tube ceiling. You can see the lava flowing inside. This is a little different. You have some kind of hole. It could be a hole, it could be a fracture, and then you have a bunch of lava flows that come, and they can come at any time, millions of years later, and form a stack of lavas. But because of that void down deep, you have a structural instability, and you have a cave-in that eventually happens through that whole series of lavas, and you expose them all inside the hole. So there I was thinking about this. This is back in 2015, maybe, looking at this hole thinking, wow, it would be really cool to explore that. I think a lot of people are thinking that. But then how do we actually do it? The thing, of course, I don't build moon bases. I'm not looking for monoliths. I'm a geologist. What really got me about this hole was not this picture of the void and the dark unknown, but this oblique picture, little blurry, of the layers that were exposed in the walls of this hole. And I said, wow, that is a lot of rocks. That's tens of meters of beautiful, pristine, exposed bedrock. That is something that I'd like to check out. And the reason that this is so exciting is because unlike on Earth, where you have bedrock exposures all over the place, is your guys are especially lucky here in Arizona. On the moon, almost the whole moon is covered in this blanket of regolith. So all the smashed up rocks, and you can't really get a view of how they were originally laid down. So my life changed when I met Isa Nesnis, who's a robotics engineer at JPL. He is the inventor of this rover called the Axle Rover. And the way that it works, it's a two-wheeled rover. It has eyes in the front there. All the instruments go in the payload bay. The payload bay is the wheel well. And then it's got this boom, and out the end of the boom is a tether, and it rappels down the sides of cliffs. And so I met him one day at a cave enthusiast lunch at JPL. And he said, yeah, I have this rover. It can go down steep slopes and cliffs, and I'm not really sure what to do with it. And I said, wow, if I were you, I would send it to this amazing moon hole that they found on the moon. And he thought, okay, that's a cool idea. And so we started writing proposals about it. Here's a little bit more of the rover. Here's it working in a quarry out in the desert. And then here's kind of how it takes its measurements. It has all of those instruments in there, and it sort of cycles through them like a lazy Susan and then puts the instrument out on the ground. which is great because it can protect the instruments from all the dust and banging around that they would get normally rappelling down some kind of slope. So we sort of started thinking, okay, what if you actually wanted to make this a mission? How does that work? So first you have to have an idea. We had one of those, and we found some like-minded individuals. Then we had to see, okay, it seems like it would work, but would it actually work? And then we had to go to JPL and say, hey, we have this idea, what do you think? And then I remember the first time we went to JPL, they said, if your robot doesn't descend down an ice fissure in the South Pole of Enceladus, I don't want to hear about it. And so they're like, come back in 3 months. So we'd come back in 3 months, like, oh, how about now? Come back in 3 months. So finally they said, okay, I think we like this idea. So they gave us a little money to sort of figure out, could it actually be possible? So we got a little bit of money. We developed the technologies a little bit further, but still, every time the devil is so far into the details. Is it actually going to work? Can you do what can you actually do with what you have, and then can you afford it? And then you submit it to NASA. So in 2019, we went through this whole process. We submitted a proposal to the Discovery mission call, and we got to final proposal, which is like probably 19 or 20 missions. But we didn't make it to the final 4, which were the 2 Venus missions, Io mission, and the Triton mission. It's really cool. And then we got 2 Venus missions out of it. And so we're like, okay, it's like the Olympics. We have 4 years to train. In the meantime, have a baby as fast as you can, as I'm doing, until Moondever comes back. And so here's a picture of the like-minded individuals from our team. And there's actually a lot of Arizona State alums here. We have Brett Denevi is there. She was the deputy PI of the mission. Patrick McGarry was one of our engineers from the engineering school here. Robert Wagner is actually here at ASU, did a lot of really important stuff for us. He was the real guy finding all of these moon pits, and you should read all of his papers about them because they're amazing. And then James Ashley is also another ASU alum over there. And I'm sure there's more. So all of you can help us do this mission someday too, hopefully. So the idea, okay, got all these people together. What do we actually have to accomplish? We have to land somewhere near this giant pit, but not in it. That's important. Then we have to get our rover off of the lander, and then we have to rappel down this giant cliff into, get all kinds of awesome PR shots and transmit the data back to Earth, and then explore the moon cave below. And the other tricky thing about, actually proposing a mission to go to a cave like this is that that cave, you can't, by definition, you can't see what's going on down there. You don't know if it's a giant cave or a lava tube, or if it's just an alcove. We know it goes back maybe 20 meters, but we don't know how much further it goes back. So if you want to make a mission that's specific purpose is to explore the cave, it's hard to sell to NASA because you have to say, we don't know anything about it. We want you to trust that it's a real thing that we're going to go explore. And so for us, it was much easier to say, we are going to explore this beautifully exposed giant cliff of stratigraphy. And then we have a lot of extra time. With that extra time, we're going to explore this mysterious moon cave. So here's another way of putting this with some more numbers on it. We have to kind of land. JPL has been working a lot on their precision landing capabilities. Some of this was demonstrated with the Perseverance rover. The moon is actually easier because it doesn't have a parachute phase and it doesn't have wind. And so you can land pretty precisely on a spot, and then you have to rove there, but it's a rappelling rover, like I said. It's attached to a tether. The tether provides power and provides communications, and it provides the structural strength that you need to rappel down this wall. And this tether is actually only about, I think it's like 5 millimeters thick. So it's pretty amazing. So you have to land close enough to that pit so that your tether's long enough, but far enough away so that you don't fall in. So why would we be interested in a beautiful exposure like this? It kind of goes back to the story of planetary crusts. You probably heard of a primary crust, a secondary crust, and a tertiary crust. Primary crust is just, okay, the planet's formed, accretion, there's maybe a magma ocean. What's the first crust that forms from that process? Then you melt the interior, you form a bunch of basalts, and you resurface the whole planet. That's kind of how Mars is. And then if you get to a place like the Earth, you have a tertiary crust, you're actually recycling a lot of, you're getting the basalts back in there, you're you're refining them, you're making silica-rich deposits, and you make like a very complicated crust. So the moon is kind of exciting because it has its original primary crust that we can see, and it started to resurface itself with a secondary crust, and then it stopped. So it's one of the only places where you can go where you can see what is the original crust that was formed, and then how does the secondary crust form, and you actually get to see what it had to come up through in order to form itself, which is pretty rare. And so if you can get those lavas, the moon is like this kind of time capsule that's frozen from the beginning of the solar system. The other planets probably went through processes similar like this a long time ago. If you can get those lavas that tell you about that primary process, it can tell you a lot about how that secondary crust building process works. But even if you do get a fresh stack of lavas, which all the fresh stacks of lavas on Earth have told us tons about how the Earth's crust building system works, the lava itself has been through a lot since it's come from the mantle. And these are all things that you have to take into account when you're trying to figure out what's going on. So let me give an example, kind of an analogy. I was thinking, like, a lot of you are here in Arizona. You probably come from a lot of different places in the US, for example. If I was going to interview you all, and I want to know about your hometown, you've probably changed a lot since you left your hometown. The best way to learn about your hometown would be to interview a bunch of people that just got off a plane from your hometown, and they haven't changed at all. But like, you've been here for a while, maybe you have like Sun Devil shirt, and you have like a cactus garden and stuff like that. And if I see things like that, I can tell, wow, that screams to me Arizona, that happened in situ. Or if you're like, oh, I have a bunch of Eiffel Towers in my house and berets, like, oh, I think you stopped by Paris on your way to Arizona. And so by looking at these lavas, they're each in a state where, like, maybe some of them spent several years changing in Paris, maybe some of them came straight from their hometown. This is kind of what you have to sort out in order for them to be useful to you. So in the case of a lava, it comes from the mantle or the crust, then it comes up, it forms crystals, it stays for a while in a magma chamber perhaps, and then the eruption process itself leaves its own imprint on top of all of that. So in these two examples, I have a basaltic glass here. That's more likely to come straight from wherever it came from. It didn't form any crystals, it just quenched, and then it's frozen. And then nothing happened to it because it can also be weathered and turned into clay. And then the top one there, this has vesicles, gas came out of it, has a bunch of phenocrysts, different kinds of crystals that probably grew as it was stored in the shallow subsurface. So in the case of these, if all I care about is your hometown, I'm going to talk to these guys. And my main goal is to just sort out all of the other ones and throw them away until I get to something that looks like that. But if my goal is to learn about what the lava has been doing on its way up there in the crust, then it's really useful to have those as well. So the most useful thing is to have a whole group of them, that you and all your siblings, or you and a whole plane of people from your hometown that all had different experiences, and then I can link them. What's the common themes between all of these people? And I can figure out what's going on deep in the crust, and I can also figure out a lot about what happened since then. So when you're studying the early Earth, it's really hard because the traces that you're looking at have been through a lot. So imagine, I always think, they say that geology is like you're reading a book about the history of the Earth, but somebody tore out half of the pages. But what if somebody tore out half the pages and then smashed them in a million bits and then subducted them into the mantle and then wove them into sedimentary rock and then waterlogged them and then folded them in a mountain belt, and then that's what you have to decipher to figure out where they came from. It's really hard. On the moon, you have almost a pristine record, but it's been space weathered and it was basically shredded into a bunch of bits that we know as the regolith. So as a result, even this problem, just the shredding of this regolith, is hard because you're missing a lot of context. The nice thing about it is that if you take a big scoop of regolith and you bring it home to your lab, then you can do all sorts of things. Oh, what kind of paper is this? Where did that come from? What about the few words that I see written on the paper? What font are they in? You know, what era is that font from? You can do, and we have spent the last 50 years doing the most dedicated and detailed analyses of every piece that we can get our hands on. these are two little pieces I just wanted to show as an example. The top piece is actually an impact melt, and the bottom piece is a pristine basalt. But they're really hard to tell apart. This is a very interesting paper by Clive Neal, where in order to tell these two apart, really what you have to do is do an in-depth analysis of the trace elements. And then you find the siderophile elements, which are the iron-loving ones. There's more of them in the impact melt because it brings nickel and it brings other metals from space in the actual impactor than there are in the pristine basalt. But that's, in order to do that, you have to destroy a bit of the sample. And as you can see, these samples are really small. So what Clive Neal and his students were doing is that they were trying to figure out different ways from the crystal size distribution to figure out the difference between an impact melt and a basalt without destroying it. If you find something that's not in the regolith and it's actually in place, you already know that it's from a lava flow. You're looking at a lava flow. You can simplify it a lot. So when we're studying the lunar basalts, there's the unknown cooling time problems. There's unknown relationships to nearby rocks. Oftentimes you just have to say, I found a bunch of rocks. They could be related. I'm going to assume that they're related, and then this is what I find if I assume that. So the analogy goes that if you look at this whole sequence of basalts, you can just read them as in order. So that's really helpful. So what's helpful about it? Well, you know the provenance. You're looking at it, it's a lava, therefore it's a basalt. You know where you're taking the sample from in the lava flow. So even the vesicle distribution and the crystal distribution can be different from the top of the lava flow to the bottom, or from the middle of the lava flow to the crusts. So if you take a crust piece, that's the most likely to be the one that hasn't changed in situ very much because it almost immediately froze as soon as it erupted. And then you know that it came from the local place. In the case of the regolith, you can have a big mixing from things that were thrown in from even hundreds of kilometers away, or it could be local. You know this one's local. You can calculate the cooling time because you know the thickness of the lava, and then you know the relationship to nearby rocks. So you can pull out a lot of this stuff. This is from the same Neal paper in 2015, where you look at the crystal size distribution, for example, and you see this is the megacrysts. So this is the phenocryst, and they have one cooling rate that's from deep, in the subsurface. And then you have the other cooling rate that happens when you erupt it on the surface, and it's a really fast cooling rate. And then this example just shows some liquid lines of descent. So it shows kind of like if you had a lava of a certain composition, how would it evolve? And these dots are from Apollo 11 and Apollo 17. And these dots, I believe, are from Apollo 12. So you can see that when we take these measurements, we think, okay, the lavas from Apollo 17 and Apollo 11 could be related to each other. They could fall on the same liquid line of descent, and they're from a similar part of the moon. So that seems to make sense. If we assume they're related, then we can say blah, blah, blah. And then these seem to be totally unrelated. But if you knew that they were related, you wouldn't have to use this to prove that they could be. You would use that to prove other things. So what we're ultimately after are a couple different things. One, we don't know the interior structure of the moon like we know the interior structure of the Earth. We don't know if it has a mantle that's homogeneous, how homogeneous the crust is. We don't know a lot of things about the layering of the moon, whether it's had a mantle overturn. And then once the lava is formed, where is it formed? Where does it come from? And then how does it get up through the crust? And does it stay anywhere for a long time? Like the moon doesn't have a lot of giant calderas. That generally tells us that you don't have a lot of storage of moon lavas in the shallow subsurface. But these are the kind of things that you can sort out. And it's important to us to understand these kinds of lavas because the formation of the secondary crust, and in particular these enormous flood lavas that we see all over the surface, they only make up about 7% of coverage of the Earth, because the Earth is constantly renewing itself. But on other planets like Venus, flood lavas make up 60% of the surface, over 40% of the surface on Mars. And so it's a very common type of lava throughout the solar system, but one that we don't have that many examples of on Earth to study. and certainly not in a case where we have a beautiful primary crust and we can study what it comes up through. So if you wanted to actually do this and understand some of these questions, which ones can you actually get at, and how would you do that? This sort of engineering and implementation part. This is how we started going about it. First, we built a wall so the Axle Rover could climb on it. We could actually practice putting our instruments down on the wall to see what kind of quality of data that we would get. We practiced rappelling the Axle Rover itself down the wall. There's a lot of mobility challenges with working in a vertical environment. This is Patrick McGarry and his team of engineers that were working on the Tether, which is our lifeline. And we, in this picture here, we have actually an instrument I'll show you in a minute in the vacuum. So here's the instruments that we decided to take and kind of how they fit inside of Axle. We wanted a set of cameras, one that can look at the wall right in front of us, and then one that can look at the far side of the wall that's behind us. Well, I guess a pair that looks in front of us for stereo. And then inside the wheel well, we have a microscopic multispectral imager. It's a microscope, but then it also gives us a spectra for every single one of those points, so we can see mineralogy, an alpha particle Xray spectrometer, which gives us the elemental chemistry, and then a surface preparation tool, which we use to make a nice, beautiful flat spot for our other instruments to look at. And they can all look at the exact same spot because you kind of have them on this rotating tray. So what would we see if we looked with a far cam? I put this image in here mostly so I could show this picture of Addy Keller out in the field. Some of you know him. He was also working with me, came out to Utah with me to be a beautiful scale for my picture. So in this image, what I'm showing is on this side, there's a bunch of Hawaiian lavas. They came out at a low flow rate. And so they made this complex flow field with these thin lava flows here and some slightly inflated pohoihoi flows. On the other side, that's all one lava flow, just a giant flood basalt. And there's a guy standing in front of it. This isn't a quarry. So when you're looking at the layers inside that pit, it could be either one of these solutions, but with our far camera, we should be able to tell the difference between those two. Then if you get up close, with our close cameras, you can start to see vesicle shapes and sizes. You can start to see flow boundaries, layer boundaries, inflated toes, all these sorts of interesting things that you would do with the lava up close. This is our first image. Well, it's actually a 3D model. I had like a wheelbarrow axle, and I put GoPro cameras on it, and then we lowered it over the side of a hill. And then we only had one GoPro camera, so we took a bunch of images in a row, and we were able to stitch them together and make this beautiful 3D mosaic. And it sort of helps us with data sufficiency. Like if I saw this picture, would I be able to tell that this is a pohoihoi flow? I think I would. But then would I be able to accurately measure it? And what other things could I determine? And here are some of the problems that you come across when you're doing this kind of thing. First, if you make shadows on your own self, it's actually possible to make a good 3D model out of that, but it's not easy because in every single picture you have this giant shadow that always looks the same. And then you have lens flares. If your wall is like irregular, then you can spend some time hanging. So you might spend some time going like this, and then you kind of go back until you're facing the wall again. And in our case, it was actually great because you could get a 3D model then of everything as you slowly spun around. But then eventually you want to be facing the wall so you can keep going. And in our pit, the walls are kind of like this. Then you have a big overhang. So you're going to spend a lot of time, actually, that giant overhang on your way to explore the cave, looking around. In the first iteration, I had the camera, and the engineers were saying, hey, we don't really want to move the cameras to face this way. Can they just face down and have a really wide field of view? And then we don't have to move them. And so I did that, and I put the camera facing down. But then you build the 3D model where if you're looking down, everything looks awesome. And if you're looking up, like in that picture, it's super distorted. And so it's kind of like you can talk about all of these things in the theory to people, but it really helps to have some actual data to show them like, actually, this is what happened when you do that. So here's a wall, and here's a picture of my little wheelbarrow axle. I have like a piece of wood that I attached to it, and a straw, and then like a rope and a GoPro. And then you can actually see the part of the wall that made into that 3D model. So to go through the instruments just a little bit, this is the surface preparation tool instrument. And what it is, it's a grinder. We wanted something like the rat that's on the MER rovers, the rock abrasion tool, because on the moon, you don't have alteration lines like you have on Mars, and you don't have as much dust layers, especially on vertical surfaces. But what you can have is what's called a patina. The patina is formed by little tiny micrometeorites that hit the surface, make little blobs of glass. And those little blobs of glass are partially rock and partially impactor. So they have a different elemental composition than the rock itself. So it was funny because we were trying to figure out how big of a problem is this. We actually ran into one of the Apollo astronauts, and we said, like, hey, is this a problem? Do we have to worry about this? And he said, well, on vertical slopes, and especially slightly overhanging slopes, you don't get as much of this because micrometeorites aren't hitting them. As you get further down into the pit, your sky is limited, so you have less area for those micrometeorites to come from. But it is a problem, and like this was Jack Schmidt. So he's like, on Apollo 17, he would say, oh, this looks like an interesting rock. I think it's this. I'm gonna break off a fresh piece so I can tell. So we decided, okay, first of all, it's really nice to look at flat spots because it's easy to reduce your data afterwards. You don't have to do a lot of corrections. And then we can make sure that we get rid of this patina problem. So we developed the surface preparation tool. The thing is, like the rat tool, it takes a while to work, maybe a half an hour, and it is on an arm, so you can push the arm against the surface and have this reacting force. If you're hanging from a wall, it's difficult to have a reaction force if you're trying to grind something. So we tried a bunch of different solutions, and the best one that we found was kind of like a grinding wheel, like you would use on a Dremel tool or something. And it's this one's a tungsten carbide, but the eventual one would be a diamond grinding tool. And as you grind with the diamonds, then the old diamonds fall out and you get new fresh diamonds. And so it actually works amazingly well. Now, if you imagine you're going down this 3D model here, you got to choose a spot to put your instrument. You got to figure out what the topography is like. You got to put down your surface preparation tool, and then you got to grind a little flat spot. And this one can grind a flat spot probably less than a minute, whereas, and still using the same low power like the rock abrasion tool. So here's an example. We made a patina using a laser raster. This was funny because everyone thought, could we use a laser to get rid of the patina? And we talked to some people and they were like, actually, a laser would be a great way to make patina. And so we made a patina with a laser. And then we removed it. You can see already, all of those beautiful plagioclase crystals that are revealed in the spot that we made. And then we tested it by hanging Axle from its sample wall and actually tried to do it. And then we put it in a vacuum chamber with the right amount of normal force on it and did it again just to see if it would work. What we found was you can make a beautiful flat spot, but it's a lot harder to get all the dust that you've created then off of the spot. So you kind of need a little grinder and a brush that follows on afterwards. So here's an example of that. This is the multispectral microimager, our second instrument, and I have Glenn Seller up there. Some of you might have worked with Glenn. I know he worked with Jack Farmer on this exact instrument a number of years ago. And here we've made a flat surface with the surface preparation tool. And then we only cleaned the top of it there. So you see a clean surface, the dusty surface covered in purple. The rough surface, you can still see all those beautiful tantalizing minerals, but it's a lot harder to do like a count of crystal size, frequency distribution, or all the analytical things you would do on the rough surface. But on the clean surface, you can actually see all of the red minerals are plagioclase, and the green minerals are olivine. And then the third color I chose is the dust, just because I was trying to bring out what the dust looks like. So this instrument, right now, it has a resolution of think it's 62.5 microns per pixel. And what we want to do is make it about 18 microns per pixel, so that this is a actual thin section of the exact same rock. So here's a big vesicle, and then there's a giant plagioclase and an olivine. And so if you were able to look at it with this resolution, you'd be able to pick out the size frequency of those phenocrysts from in the shallow subsurface and the tiny little microcrystals that are made during the actual lava eruption process. Our third instrument is the alpha particle X-ray spectrometer. Here's a picture of Ralph Gellert, which is our partner. He was the one that was behind the APXS on MER, the APXS on the MSL rovers. And he's in Canada at the University of Guelph, and he works at the MDA Corporation. So they're all our partners. And the great thing that this instrument does, it kind of, you have a spot of about 1.7 centimeters, and you get all of these elements out of that spot. And you can kind of see it's, like I said, the devil's always in the details. You can get all of these elements at very high precision, but then sometimes if you want, like, oh, can we get chromium, or can we get, another like titanium or these sorts of scandium? What about trace elements that we might want to do petrology with? Some of them are quite easy. They really stick out really well. And then others of them, like they might be on the side, the shoulder of that iron peak, for example. It's hard to pick them out no matter what. If you have a lot of iron in your sample, it drowns out whatever other tiny elements that you're trying to pick out. And you can tweak the instrument in different ways to like pull out the trace elements that you want. And so the cool thing is that the Canadian Space Agency funded these guys to make a new version of APXS that's suited specifically for the moon. So they're working with the sources they're using and the digitization of their signals and stuff like that to bring out the most beautiful and interesting trace elements that we expect to be on the moon. So I've been working with them on that. And then the coolest thing that you can do is if you take those two instruments, usually if you get all the elements from an APXS, you can do like a normative mineralogy for your rock. If you have all of these minerals from the multispectral microimager, you can do like a modal mineralogy from your rock. And then you can put those two together. So even if you have an integrated view of the elemental chemistry, you already know what minerals are there. It's a lot easier to figure out what composition each one of those little minerals are. And how we do that is we have our spot preparation tool, makes a big spot. The MMI field of view fits within the spot, and the APXS circle fits within that MMI spot. So you have them all co-located. Because even in the case here, where you have little tiny crystals that it's hard to see, for every single one of those pixels, we're going to have a spectrum, it's like 21 spectral channels. And so that you can see like, oh, even though I can't really tell what that is from its shape, I can tell that it's the plagioclase from its spectrum. So then, when you actually get to the moon, this is the cool stuff I was telling you that Robert Wagner is working on. Robert Wagner found all of these pits. You could go to any one of these pits, and they all have different engineering challenges. In the case of Tranquilitatis, it's really close to the equator. We actually think, based on some modeling that Paul Hain has done in his students, it might be one of the hottest places on the entire moon. We did not know that when we were starting out, and it causes a lot of trouble for our rovers. So you could go to a place like Loch Mortis, which is really far north. All of them have a trade-off of what lavas are you specifically sampling, then what is the geometry of the pit like, what's the thermal environment like, how is it illuminated, is it accessible, is it on the far side of the moon, so you'd have to have a relay. All of these things kind of play into your decision. So we focused mostly on the Tranquilitatis Pit. This is where it's located. I wanted to show you there's Apollo 11 and Apollo 17. So we actually have samples of the lavas that we think are involved in this situation, which is very helpful to us because suppose you get all the context you're looking for and you have samples in hand, you can go very deep and you can have the broad context as well, kind of helping you out. So we would have to pinpoint land. I talked about that. Well, our partner here was Lockheed Martin. They're making some beautiful moon landers. based on the InSight and Phoenix landers, and then rappel down the side. You can see that Axle has changed. Its wheels are now white. That's actually a thermal thing. We had to put a radiator on Axle. And of course, as you're going down the pit, you have to look at the sky in order to radiate. And the sky's getting smaller and smaller the deeper and deeper inside that pit you go. That's why it's so hot. So the other challenges, extreme temperatures. This is especially the case if you're close to the equator, or if you're trying to work, usually lunar noon is the time everyone shuts down because it's so hot. In this case, if you're going down like the western wall and the sun is coming up in the east, western wall is blazing hot until maybe 10 o'clock in the morning, and then it's shadowed for the rest of the day. We're great in the shadow. So if you're willing to burn a bunch of mission time, you can have a lovely thermal environment. These are sort of trade-offs we have to make. So here's some models we did of the surface temperatures, and then there's the irradiance. It's great to be in the shadows, but can your camera take a picture that's not blurry? Is it light enough? We determined that it actually is light enough with scattered light to take pictures, but that changes, say if you were spinning or if you're moving, you're more likely to have blurry pictures unless you're really well illuminated. And then the contact, Robert Wagner did some great 3D modeling for us of the walls of the pit. Depending on which wall you go down, you might be in contact for more of the time than others. You might be hanging. So of course we want to pick a wall where we're likely to be in contact almost the whole time. And this is a challenge because we only have a certain number of pictures of this pit. So we're just very grateful to LRO and LROC kind of taking as many pictures of these pits as possible so we can do these analyses. Then we do a bunch of tests on the tether. Can it hang from the tether? How tough is the tether? We move the tether across extremely sharp lava rocks, for example. And then, yeah, you can see there, we were doing a test where we were trying to bend the tether as much as we could on the side of a lava rock. Then we have, like, how do we get off the lander? We built the lander. It's easy. The rover risks a repelling rover. Of course, it just repels off the rover. But what if it landed at a crazy angle? Can it still get off the rover? All these things that we're concerned about. And then here's just a beautiful picture of us taking it out in the field in California. And then this is a picture from a field trip we took with the whole team just to show them what a lava tube was like, because a lot of them had never been inside of one. This is a very tiny lava tube, and Axle can't fit in there. And then, of course, we have to operate this. And I always like to show this picture. This is the Lunicod team in the 1970s driving Lunicod rover. And it was about 5 people actually total on the team. And you can see the driver there. He's just looking at the screen. He's got like the fan up there. He's got a joystick. He's just driving it on a joystick. And one of my friends, Sasha Basilewski, he was fortunate enough to be in the room. They didn't allow scientists in the room. But then he said he just one day went there and took a chair and just sat in the room. It was like, and everyone thought that everyone else had given him permission to be there. So then he started being like, oh, maybe you should stop and look at this rock. And apparently the head of the program was like, Lunicod means moonwalker. And they're like, Sasha, this is a moonwalker. It's not a Luna stop. He always wanted to stop and look at rocks. And they said actually one time they were all worried because they lost connection with the rover. They're like, oh no, we lost connection with the rover. What happened? What happened? And someone was like, oh guys, the moon set behind the horizon. Because they were only talking to it when it was in the sky. So everyone's like, oh, thank goodness. So it's very intense. It's totally different than Mars operations. So in the case of Moondever, you have to descend into this pit. It's 125 meters deep or so. It's not that deep. It's not that far to go. But it's complicated, and you want to stop a lot, and you want to do it all within one lunar day, which is quite a challenge. If you did it like, we landed Perseverance on Mars, and then I was counting down the Moondever clock, you're probably still sitting there being like, I wonder if our rover is turned on, or like, let's check some, signals coming back and stuff like that. And like, oh, it's over. The whole mission is over. You haven't done anything. So in the case of Lunicod, they were able to drive, hundreds of meters the first day. In some days they were driving kilometers. I think total they drove over 40 kilometers in a couple of lunar months. So it's definitely possible to do this, but you have to have a whole different mindset. So in our concept of operations, we had basically like a cockpit, almost like the astronauts. So these people, they make all the decisions about what they're going to do, and you just have to train them and then trust them to make the right decisions, because you can't have a long conversation every single time you have to make a decision. Then we had a back room for anomaly resolution and for data validation. So all of the instruments would have people sitting there being like, okay, APXS got a spectrum. It looks like it's a good spectrum. We can keep moving. And then these people decide where to go. And then somebody who's overall saying like, okay, guys, we don't have a lot of time. You better keep going. And then people that deal with the telecom communications problems. And then a more back room where everyone's piecing all the data together and sort of looking at the overall view of what you found. This is what I keep trying to sell to JPL as what I want the operations room to look like. I told them they could build it underneath one of our big operations buildings, you know? And it was so funny because I was giving a talk to the director and I was like, I just want you to think about this, you know? And he was just stony faced, like, what are you talking about? And then I was like, I just want you to think about this because I think it would take 20 years to get the building permit to make it. And so I just want to let you know about it now. And then he was like, ha, 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 ha. Building permit joke. Are so funny. So just to tell you about the future of Moondever, I like to say that Moondever is a mission that does not exist and may never exist. We are submitting it again to the 2023 Discovery Round. And then we'll just keep submitting it if they keep accepting it. But what I really hope is that Moondever is kind of a vehicle by which we can move a lot of these ideas forward, technology development, science implementation. We're going to be spending a lot of time over the next year doing field tests and testing a bunch of lava sequences with Moondever's instruments. And so what I hope that ultimately will happen is some mission like Moondever in my lifetime will go to a lunar pit and see what's down there, because I think it would be very exciting. And I was talking to Bruce Bannard. I think you guys had him as a colloquium speaker recently. And he was the one that kind of kicked me off on this whole thing, because he said, yeah, I thought of the idea for InSight like about 30 years ago. And it took 30 years to get it finally to go. And so at the time, you know, I was like 30, and I was thinking, oh, I better hurry. I better start now. So I think we even got a bit further than I expected on our first round, and we will see where we get in the future. So I hope you all can come to JPL at some point and help us out working on it. Thanks, and I'll take any questions.
So we'll take questions from the room, and also those of you online, if you put questions in the Q&A, we'll pick on some of those too. So questions from the room. There's one right up here.
Hi, Laura. It's Hannes Bernhard. Hey, how do you make sure the lander unit doesn't get pulled along on the loose regolith, you know?
Sorry, how do
you make sure the lander
yeah.
doesn't get pulled along with as the rover descends?
That's a good question, and we did an analysis on that because we were also worried. The first answer is that it's very heavy, and so compared to Axle, it's just many times more heavy, and so it's hard for Axle to move it no matter what Axle does. But then, in addition to that, we kind of looked into, could you make its feet kind of like a wedge shape or something like that, so that you would do it? And they kind of ran the numbers, and they said, yes, it would help to do that, but it's already so hard for it to move that they don't think it's that necessary. Yeah, you are limited for how tilted terrain you want to land the lander on, because if it's really tilted, you're more likely to pull it over. But you're limited anyway to less than 15 degrees just for a safe landing. So you land someplace flat.
Hi, thank you for the nice talk. Have you considered the idea of wireless communication in case you're too far away and then you don't have access to tether, or something wrong happens with the tether, just as a backup option of a battery on the axle, and also being able to communicate from outside?
Yeah, so actually the field version of Axle had a wireless communication because we didn't have the tether up and running yet. So, and people have been building a lot for wireless communications on the moon, so it's not impossible. In our case, if we lost our tether, I mean, we would fall in the pit. So what we did is we just made a very redundant tether where inside that tiny little volume, we have multiple strands of each kind of thing: power, comms, and strength. And so in the end, it's actually quite robust. But you're right, you could do it. The problem we had in the real pits on Earth is that you have to have kind of a tall tower, so that as it gets deeper in the pit, it can still have a line of sight with the wireless communications, because it's hard for it to then communicate through the rock.
A couple of questions online. How is the rover powered?
The rover is powered with the solar panel that's on the lander, and then the power goes through the tether to the rover. And like I said, the rover has a small battery. Yep.
Yeah, okay. So I just want to know what material is the tether made of, so that doesn't snap?
So it doesn't snap?
Yeah.
Yeah, that's a good question. I remember we went through a lot of different exotic materials. There's like Kevlar and then Vectran and then this and that, and each one of them has like Vectran is very strong, but then it's bad for UV light or something like that. So I don't remember. I have to ask Patrick McGarry, he was the tether guy, what we ended up with as finally the strength member of that tether. But we had to test it for abrasion, for thermal cycling, and for it's sheathed to protect it from the UV, but like you also worry about the UV exposure on the moon.
Yes.
Okay. Okay. Oh, now it's working. My bad. This might be kind of a dumb question. You mentioned that you are limited to doing this all in one lunar day, and I was just wondering where that limitation comes from.
Yeah, that's a great question, because there have been missions that have survived the lunar night, like Lunicon, for example. It was carrying polonium radiogenic source, so it heated itself overnight, so that if you stay overnight, it gets so cold that all your wires become kind of brittle, and you risk damaging this craft. So either you take a lot of batteries, and batteries don't do well in the cold, so you have to take a lot of batteries, and you heat yourself overnight, or you bring like a radioisotope source that heats you, but it's expensive, and the most expensive part, honestly, is all the paperwork you have to fill out to launch it. And so we try not to do that. And then, there's some ways to make a spacecraft survive over the lunar night without doing any of those things. Like some of the Surveyor landers back in the 1960s actually just survived the night, even though they didn't intend them to. And it's just making like robust connections and double wiring things and not moving it a lot at night. In our case, if you put the Axle Rover, which is the delicate part of this operation, into that cave where it actually doesn't get cold at night, we think that it might survive. So if you made the lander as simple as possible, the lander managed to survive, you could probably operate in a second day. But knowing that we had plenty of time in one day to make the short journey, we were kind of like, let's try and fit it in that time. We know that we'll get that time. If we get a second day for cave exploration or whatever, then it's a bonus. It's just a risk posture.
We got another online question. Let's just make sure folks online
Sure.
get a chance too. If you could choose one more instrument to place on the rover, what would that be, and what would it measure?
Well, so there's a lot of instruments that would place on this rover. In the very beginning, I thought, oh, you know what I want to put on it? Like a drill system and a mass spectrometer or something that would measure like chronology, for example. That would be amazing. But those are really expensive, heavy instruments. They require sampling, so probably not. The other instrument that we considered putting on it was a magnetometer, because we're going to really ancient lavas of the moon, and it's probably during the time period when the moon's magnetic field is active. And so you could take the magnetometer down with you and see the magnetics of the stack. But that's also hard you have to kind of isolate that magnetometer from lots of other electrically made magnetic fields on your spacecraft for cleanliness. And so it's difficult. In the end, we're kind of most limited by cost.
How many models did you have to go through before you agreed on the Explorer model you have now?
The Explorer model, you mean like the rover?
Yeah.
So it's actually a lot different than how it started. ESA started developing it back in maybe like 2002. And back then it was a bunch of different axles that you could hook together into a long train. And then he made a kind of a bicycle wheel version with big paddles on the side. And then this is kind of 3rd/4th generation axle. And I think the ultimate axle would be even an iteration beyond that. Like the grout, we'd changed some things about the grousers, and we had to put the radiators on. And so on paper, there are many more iterations than there were that we actually built. But this built version is probably version 3 or 4.
We're going to wrap up in just a minute because Professor Busick, who teaches the colloquium class, needs to meet with the students right after that. So we want to end on time today. So for those of you who are in the class, stick around. We won't stop the Zoom meeting early by accident like somebody did last time. That was me. Another question from online. Do we know what starts the cave-ins that make these pits? Is it spontaneous or could they be kick-started by something like an impact event? So we'll do that question, maybe one more from the room, and then we'll wrap up.
That's good. So they could be spontaneous. If you have an earthquake, that's a perfect way to cause a cave-in. And the moon has moonquakes, but then it also has impact generated moonquakes. So I think the cave-ins most likely caused by seismic shaking due to impacts. And some of these, like the one in Hawaii, actually started looking like a bottle like this, and then over time collapsed backwards until now it's like a cylinder. And so that's the way these things form. They collapse at their rims. And so the most dangerous part for this rover is really going down that funnel where there's probably a bunch of cracks that haven't been touched in a long time.
And one more question from the room.
Hi, thank you for this talk. So I had a 2-part question. What is the projected mission lifetime for something like this? And are there any instrument redundancies you're particularly worried about?
So the projected lifetime is, we have to get to the moon, which might take a couple months if we go the long way. And then you land on the moon, and then it's only 14 days at most. You might land a little bit after dawn. And then that's the nominal mission. Maybe you'll survive to a second lunar day, but you don't know. And so simultaneously, you do have to be radiation tolerant enough to survive that traverse that goes out 3 or 4 months into space and comes back. But the actual working lifetime of the instruments is very short. And so like the number of times that grinder has to grind is only, a couple dozen, maybe at most. So for the redundancies, there's kind of like a functional redundancy and an actual redundancy. With the cameras, you have 2 cameras, so those are fully redundant. But then like the MMI instrument, for example, is also a camera. So if you have 2 cameras and you lose one of them, then at least you get some of the data that you were looking for. It's a Class B mission, so we do have to have a lot of our subsystems have redundant like wiring and stuff like that. But then other things that we're only single string on, like our lander doesn't have a lot of redundancies. That's kind of risk that we just have to take in order to fit into the box. I think what I'm most worried about, it was always for me a thermal because we have such a challenging thermal environment. If we chose a different pit, we could not have such a challenging environment. So, yep, that's my answer probably to that.
Great. Well, thanks. And let's thank our visitor again for a great talk. Thank you, Laura. That was awesome. And thanks for coming to visit us in person. And those who are in the colloquium class, stick around. We will put Professor Busick on the screen here in just a second, and we'll be able to discuss the class a little bit. Yep. Thank you.